Welcome everyone to Professor Sim again. Today I'm going to show you the Diffie-Hellman Key Exchange protocol. So let's start with what is key exchange and how does key exchange help us. So one challenge we have when it comes to symmetric encryption, symmetric cryptography, where Alice or the base will generate a key and then Alice would want to send this key to Bob because both of them will use the same key to decrypt and encrypt in their system or whatever the method they use. Maybe the channel, one challenge is that is the channel actually secure? What if someone is able to get this key, like eavesdrop and then get the key, etc. So Diffie-Hellman is a protocol that can be used to solve this problem, where Alice and Bob can share with each other some parameters or like their public keys and come up with the shared key using some properties, as we will see in this video. Of course, we learn more once we see the implementation itself. So let's start. So Alice and Bob will first start with agreeing on two variables. Let's say A, variable A and Q, where A is a very large prime number and where A is a primitive root of Q. What does it mean for A to be a primitive root of Q? Let me show you this. It means that for A to the power of some number K, it's congruent to R mod Q, where R is also some number. Maybe this is not like making sense a lot. Maybe it would be a bit like complicated. I'll make it easy for you. This is very simple. And what's the benefit of A being a primitive root of Q is having a larger set of unique numbers, unique patterns, etc. Remember, you understand everything the moment I explain it, okay? So we even have this table that makes everything even simpler and easier for us, okay? So if we have A, okay, and we have 8 to the power of 1, 8 to the power of 2, till A to the power of Q minus 1, 8 to the power of 1 mod Q, 8 to the power of 2 mod Q, etc. till 8 to the power of Q minus 1 mod Q. The results shouldn't generate a pattern, shouldn't generate some type of predictable numbers, etc. Like it would generate some type of a range. So the attacker will be able to guess or be able to have less options to try with. According to this table, if you can see this table, for example, okay, if we choose A as 1, so let's just take another one, okay. Let's take 7. What if A is 7 and Q is 19? Okay, A to the power of 1 mod 19 is 7. A to the power of 2 mod 19 is 11. A to the power of 3 mod 19 is 1. Okay, as you can see over here, we have these. A to the power of 4 mod 19 is 7 again. A to the power of 5 to the power of 8 to the power of 5 mod 19 is 11. 8 to the power of 6 mod 19 is 1. Can you see there is a pattern? So for the attacker, finding or trying to guess or brute force might be simple for him, etc. Meanwhile, if we choose our Q as 2, for example, 2 to the power of 1 mod 19 will give us 2. 2 to the power of 2 mod 19 will give us 4. We can see a unique pattern. Nothing is being repeated in a pattern way. Some numbers are not even repeated again. You see what I mean? Yeah, this is why we take primitive roots, to have a larger set of numbers. So now that we have agreed on A and Q, let's move to selecting our private keys. So A will have a private key, XA, and Bob will have his private key. Let's even delete what I have written over here. So B will have his private key, Bob will have his own private key, and A will have her own private key again. Here we have the private key of Bob and the private key of Alice. Now, using this private key, Alice will generate her public key. The public key of Alice is equal to A to the power of her XA mod Q, and Bob will also generate his public key, which is also equal to A power of his private key mod Q. Remember, no one has the private keys except the owners of these private keys. So Alice's private key is not shared with anyone, and no one should be able to have access to this private key. Okay. Okay. Now Alice will send her public key to Bob, and Bob will send his public key to Alice. Now, according to the, let's first generate the keys. Okay. So how can Alice generate the key? Her key should take, let's call this secret key, SK. It's equal to, now we should take Bob's public key, which is YB, and raise it to the power of her private key, mod Q, and Bob will also do the same thing. SK is equal to YA, his private key, mod Q. Now here, they both have shared secret keys that are unique. Let's prove it real quick. We take the left side. SK is equal to, what is the value of YB? YB is equal to A to the power of private key of Bob, power of XA mod Q. Also here on the left side we have SK, public key of Alice, which is equal to A power of XA power of XB mod Q. Can you see that both of them are equal to XB times XA mod Q, which is the value of the secret key? Here, only Bob and Alice can have the same secret key. And I have even proved it for you down here. So what happens after choosing or having this secret key? Now they can be able to share and use this key for their symmetric encryption, for example. Especially that now we can like communicate the key without actually communicating the key as a secret. Oh wait, actually I have to also elaborate on how this algorithm is actually secure, especially that I'm sharing the public key. So what is public? Let's say what's public, okay? So what would be public is the public keys, of course. Let's say YA, the A, and the Q. Okay. If the attacker has these three, according to the discrete logarithm problem, which says, let's write this down again, public key A mod Q. If the attacker has public key or this variable YA and the A and the Q, according to the discrete logarithm problem, it's computation infeasible for the attacker to find the power or the exponent, which is the main secret of the private key. Yeah, this was a quick thing I wanted to elaborate on. Even here, as you can see, the same thing happens again. If the attacker has Q, A, and public key of Bob, it will be computation infeasible for the attacker to find XB, which is a mathematical challenge. It's like a mathematical challenge for the attacker to solve this, and no one has been able to prove that he can solve this challenge, which is why Diffie-Hellman is actually secure. Thank you for watching, and in the next videos we're going to explore more of it. Thank you.